Hello guys, Assalamualaikum warahmatullahi wabarakatuh and a very good day. So today I'm going to make a video on again supercapacitor but episode 2 about the galvanostatic charge-discharge or well known by GCD 3 electrode system. So after episode 1 we have studied about the cyclic voltammetry for 3 electrode system. Net analysis that you need to proceed is galvanostatic charge discharge. So what is GCD? So basically a GCD is an analysis where you key in your potential window and make sure your potential window must be the same with the cyclic voltammetry. If your cyclic voltammetry have the potential window from 0 to 0.5 and your GCD must also have the same potential window which is from 0 to 0.5. So the main important things about GCD generally, we're going to see first about the shape, and second, we want to see about the discharging time. Okay, that's the important thing about the GCD. So first of all, what you need to do is you need to define the current density. Depends, you study about gravimetric or areal capacitance. If gravimetric, your current density is ampere per gram. If you study about the areal capacitance, your current density is ampere per centimeter square. So depends on your study. Okay. So for example, we study about the gravimetric capacitance. So ampere per gram. So define your current density. So the meaning of define is what current density you want your sample to be run on. For example, either 1 ampere per gram, 2 ampere per gram, 3 ampere per gram, 4 ampere per gram, and 5 ampere per gram. A minimum should be 5 and above. Okay, if you already define your current density, you can obtain the value of current. So for example, I define my current density. I want to run my sample at 1 ampere per gram until 10 ampere per gram. So what I need to do is to get the value of current, to be insert the current value into the potential stat. What I need to do is I have the value of the mass of my material. So because ampere per gram equals to current density, when you have the value of your mass, to get the ampere, you need to have the mass times with the current density. So when you do like that, you can actually get the value of current. So let's do a quick calculation, for example. Okay, so we have ampere per gram. So for example, I want to do 1 ampere per gram. My mass is 1 gram. So if I want to get the current value, so what I need to do is my mass, which is 1 gram, times with 1. So I got my value of current is also 1. So in the experiment, in actual experiment, the value of mass is not 1 gram, it's very small, around 0.5 milligram, sometimes it's 0.5 gram, 0.2 milligram, and so on. So depend on your mass, you got the mass value time with your current density, then you get the value of current. Okay, it's quite easy in terms of that. That is number one. So after you already define and get the current density, you define and already get the value of current, then you can run the experiment. It's quite easy. Just determine the potential window, the same with the cyclic voltammetry, and put the value of current. So what happened is, then you can see a shape is coming out. In supercapacitor, there is specific shape. Same with cyclic voltammetry. So for cyclic voltammetry, you can have a very good EDLC like shape, which is a rectangular shape, either quasi shape, or you can get battery type. The same things for the shape we want to determine by GCD, galvanostatic charge discharge. Okay, a very what we call that carbon-based material. Theoretically, you should get a pyramid, a very good triangle. Did you ever go to the Egypt? You see the pyramid? It should have a very nice triangle-like shape. This belong to the criteria for carbon-based material. If your triangle, the line is a little bit distorted, it's not symmetrical, it's distorted, so it's belong to the pseudo capacitor behavior. It's quite easy. And if you have a battery like shape, you need to have a plateau. The shape is most probably have you goes to the wedding, you see the dome. The dome is what we call that like the place that the shape is like this lah. Normally the triangle, you have a nice triangle, and at a lower potential is plateau like this. It's plateau. So that's the shape for battery type shape. It's like the shape of the domes in the ceremony and so on. So that's number one, is about the shape. So identify and analyze the shape. It should be consistent or parallel or in agreement with the cyclic voltammetry. So normally people discuss the plateau should happen the same potential when the oxidation and reduction occur at what potential. It should occur like that. If not, plus minus a little bit off is also is also possible. So number one, shape. Okay, number two, when you run at different current density, so you got the value of your specific capacity or specific capacitance, you need to compare. Okay, so the trend, if you do the experiment when you increasing the current density, for example, from 1 ampere per gram to 10 ampere per gram, the value will slowly decrease. The specific capacitance will degrade gradually. It's not significantly, but gradually. If significantly means that the sample is not so good, because it might be due to a lot of voltage loss or IR drop. So the tricky part is about IR drop. During discharging, you can see that a little bit, what we call that, a little bit missing in terms of your voltage. Some get, some said it's about the voltage drop, some is about IR drop, because it's the same, because V equal to IR. Okay, because this voltage drop of IR drop happen if your sample of your composites have higher resistance. So you need to compare with the electrochemical impedance that we will talk in another episode. So it's different episode. So be careful when you run a GCD. You might face this kind of problem, which is a big IR drop. So in order to avoid that, make sure your composites is not your composite must be very conductive. You must dope with something very conductive to avoid that cases. Okay, that's challenges number one. Challenges number two in GCD that you might face is about what we call that about. Okay, challenges number one is about IR drop. Challenges number two is about your material doesn't able to achieve that potential window. Okay, but this is rarely happen, because only at certain substrate it is difficult to achieve that potential window. For example, in your cyclic voltammetry, you run from 0 volt to 0.5 volt, but at GCD, strangely or surprisingly, it cannot achieve 0.5 volt. Sometimes it only can achieve 0.45 volt, 0.48 volt. Okay, this case often occur when you are using nickel form. Okay, if you don't believe me, try using nickel form. So then you might face this kind of situation. If you read a lot of paper, sometimes they just make it negligible. They just proceed with 0.45, 0.48, but you need to try your best to get the exact potential window like your cyclic voltammetry. Okay, that's scenario number 2. Scenario number 3, your discharging time is too fast. For example, from 1 ampere per gram, you only get around 60 seconds. Then you increase to 2 ampere per gram, it's dropped to 10 seconds, 8 seconds, and so on. When your discharging time is too fast, when you put the value into the formula, your specific capacitance or specific capacity will be very, very bad. Okay, so it is a lot of trial and error to optimize your sample. So your sample can be charged and discharged optimally. Okay, that's scenario number 3 because your discharging time might be too short. Scenario number 4 rarely will happen, but it might happen. Charging and discharging, the shape is non-uniform. So when the shape is non-uniform, like we call that non-linear triangular shape, so it might affect your overall discussion about this analysis. So the ideal one, charging and discharging, it should have linear triangular shape or linear shape. Okay, so it's important because logically, when we talk about logic, we want to have a short charging and discharge. The power can be discharged longer. That's a very good one. But the ideal one, charging and discharging, the shape should be similar. Okay, that's the case. Okay, I think that's a lot of problem that you might encounter using galvanostatic charge-discharge. So what is the tips and tricks? Okay, so at the end of the video, I will share to you the tips and tricks when you measured your analysis using galvanostatic charge-discharge. Okay, if you have a lot of sample, you already optimized using cyclic voltammetry, just go for the optimized one. No need to run for all sample for different current density. Because unlike cyclic voltammetry, galvanostatic charge-discharge might be a little bit tiring because the process takes a longer time. So just choose the optimized sample. If you have 3 optimized sample, just run these 3 optimized sample at different current density. That's number 1. Tips number 2, you need to try at high current density first. Okay, for example, we try at 10 ampere per gram, then you need to going down slowly to 9 ampere per gram, 8 ampere per gram, 7 ampere per gram, until 1 ampere per gram. So you can see the trend from very fast discharging time, then the time increase slowly. You need to see the trend. If let's say you try from 1 ampere per gram, but in some cases, your sample cannot achieve that 1 ampere per gram. So you just wait for 1 hour, 2 hours, and 3 hours, nothing happened. You're wasting your time. So better start at high current density first. Okay, last tips and trick. Never, ever, and never do what we call that rojak. Don't skip the current density. For example, okay, now you want to run from 10 ampere per gram. Then you run from 5 ampere per gram. Then you run from 6, 7, cannot. You need to do it sequentially. You cannot jump between potential window. You cannot jump between the current density. So the results might be inaccurate. Okay, so based on the tips and the trick, I hope you can successfully plot your GCD for 3 electrode system. See you again in the next episode. So that's all for episode 2, GCD 3 electrode system supercapacitor. Bye.